This next section of chapter 6 is all about Hess's Law. So first we're going to talk about what it is, and then I'll show you how to use it to solve a problem. So Hess's Law says that if you have some reactants that turn into products, their delta H, the enthalpy of that reaction, is going to be the same whether you write it as one step or whether it's a series of steps. And we haven't really talked about the series of steps. It's called the reaction mechanism to show the overall reaction yet. But so just as a side note, most reactions are not one step, even though we write them that way. We write some reactants, we write a product, we write one arrow, and we show the reaction. But in reality, most reactions involve a series of steps. And you may have seen this if you've studied earth science at all. When you talk about the atmosphere and you talk about ozone, which is O3, there's a series of steps that happen to create that ozone. But sometimes we just write it as one step and combine all of the smaller steps. That's called the reaction mechanism, and we combine them into one step. So Hess's Law says that if you have some reactants and you have a product, you're going to have the same delta H whether you show it as a series of steps or as one step. So what we can do with that is to talk about the series of steps and look at their delta H's, and then we can calculate the delta H of the overall reaction from that series of steps. So let me go through some examples with you, and I think it'll make more sense. Okay, so first of all, there's some rules when you're solving these reactions or solving these problems. If you flip a reaction, then you have to change the sign of delta H. So if you flip a reaction and you have a positive delta H, you're going to make a negative. If you multiply a reaction by a number, you have to multiply the delta H by that same number. And anything on both sides of the arrows can cancel, kind of like when we did the redox balancing. And then finally, once you have all of your reactions rearranged the way that you need them to be, you can add up their delta H's to get the delta H of the overall reaction. So this is our first example. And this is actually the first example on your progress check. So you might want to just take a break from this for a little bit. You'll forget what the answer was. So you can practice it again on the progress check. But this is the first one. I just wanted to walk you through one of them. So first of all, here's our overall reaction. So I'm just going to draw a line to separate it so you can see the reaction from the series of steps. And then those two reactions under it are the series of steps that actually happen when hydrogen peroxide decomposes. H2O2 is hydrogen peroxide. So what I usually do is just go left to right in the overall reaction, and I make sure that the series of steps has what I need on the correct side of the arrow with the correct number of molecules. So for example, in the overall reaction, I want 2 hydrogen peroxide molecules on the left side of the arrow. So now I'm going to go down to the series of steps and find any place that there's an H2O2. And I see it right down here. And it is on the left of the arrow, so that's good, but I need 2 of them. And right now I'm only showing 1. I don't see it in any of the other reactions. So what I'm going to do is multiply that whole reaction by 2. So now we have a 2 here, a 2 here, and a 2 here. But Hess's Law rules say that you also have to multiply the delta H by 2. If you multiply a reaction by a number, also multiply the delta H by that number. And that goes for fractions too. So if you multiply something by 1/2, or it's the same thing as dividing by 2, you would do the same math to the delta H. All right, so we're good on hydrogen peroxide. So let's go to the next one. We need 2 liquid waters on the right. So let's scan our reactions, and I only see liquid water on the left, but I do have 2 of them, so that's good. I just need to get it on the right. So what I'm going to do is flip this whole reaction. And what I encourage you to do is to rewrite the reaction, because it's really hard to visualize what's going on with that if you don't have it rewritten. I'm just going to leave out the states of matter because they're all the same for this, so that like there's not gas water and liquid water, it's just all liquid water. So all right, so now we've got our new reaction here, and the rule for that is that if you flip a reaction, you're going to change the sign of the delta H. So over here, the delta H is positive, so we are going to make that a negative now. It is no longer positive. All right, so this one is good. We should have 2 liquid waters on the right. And the last thing is we need 1 gas oxygen on the right. Now, the problem with oxygen is that I see it in several places down here. Whoops, I was just trying to figure out what's going on. I put a 2 here, and this should just be a 1. We didn't multiply that reaction by 2. They just happened to have 2's already for the hydrogen in the water. So we need 2 we need one oxygen on the right. And notice that we actually have it in two places. We have it right here and we have it right here. And the other rule for Hess's law is that if you have something on both sides of the arrow that's the same, you can cancel them, just like we did in redox. So this one oxygen is going to cancel one of these two oxygens and leave us with just one. And so now we have one oxygen and it is on the right of the arrow. So we're good on oxygen. Once you have all of your molecules arranged correctly, everything that's not in the overall reaction should cancel if you did it correctly. So notice that we have two H2s over here. That cancels these two over here. And we've got this left over and this left over and then the oxygen. So we're good. And so now what we're going to do is to add up the delta H's. But now we have a negative 571.6 kilojoules per mole. We're going to add that to 2 times 187.8 kilojoules per mole. And once you do that math, you'll get your final delta H. And that will be the answer for the problem. Let's do one more just to make sure you got these. All right, here's our overall reaction. Let's start with the HCl. We need one HCl on the left. I only see it one place. It's in the last reaction, but it's on the right. So let's rewrite this one. And don't forget to change the sign of the delta H, so this is going to become positive. All right, so HCl is now good. Let's go to the next one. We need one NH3 on the left, and I see one H3 on the left. Let's circle the things that we want to end up with. That looks good. We need one NH4Cl on the right, and right now I see 2 on the right. So we need to multiply that reaction by 1/2, or basically divide everything by 2. And that will give us 1 here. Don't forget that whatever you do to the reaction, you're also going to do to the delta H. So we're going to multiply that by 1/2. And that should give us what we need here. All right, let's see if everything else cancels. We need half of an N2 to cancel half of an N2. That looks good. We need 1/2 Cl2 to cancel 1/2 Cl2. And then you get to that H2 and you're like, wow, it's all over the place. So let's see what's going on here. We have 3/2 H2 right here, and we have 1/2 right here. And those are all on the right. So hopefully you can do some math with fractions. 3/2 plus 2/2 is 4/2, which is 2. So those two are going to combine to make 2 H2s, and that's going to cancel these 2 H2s. And so they do all end up canceling. And so now you're just ready to do the math, and all you're going to do is add up all of these 3 to get your final delta H. Just don't forget to multiply the middle one by 1/2, and don't forget that the last one is now positive instead of negative. All right, just a couple more things. We mentioned standard state in the last video. Standard state conditions means that if you have a gas that's at a pressure of 1 atm, the temperature is 25 degrees Celsius, and you have 1 mole of it. And to show that it's in those conditions, you're going to see it looks like a degree sign, that little 0 up high, and it'll be a superscript. So if you see that delta H with a little superscript up there, that means that it's in standard state conditions. Also, if you have a solution, it also means that it's 1 molar. And then for an element, it's the form where the element exists in those conditions. So it's just a specific, some specific conditions for something, and it's a shortcut way to write it is with that little circle on it. So what you're going to see is actually, we talked about this a little bit last time. The enthalpy of formation is the energy that's involved in forming 1 mole of a compound from its elements. So it's a really specific definition. It has to be 1 mole. You're forming 1 mole of a compound from its elements when all the elements are in their standard state. So if you take all the elements in their standard state and combine them into 1 mole of compound, the energy that's required to do that is the standard enthalpy of formation. And so now we've got lots of things. Delta H is the enthalpy of formation, or enthalpy. The little subscript F means the enthalpy of formation, which means you're forming it. That little superscript means that everything was in its standard conditions. And don't forget that we're always trying to make 1 mole of product. So these are just a bunch of symbols. I just wanted to make sure you understand what those symbols are. And so now we get to this equation that we actually talked about in our last video, because it's kind of throughout this chapter, but this is one way that you can solve for delta H for the reaction, and this is just the actual equation for it. So Let me just show you what each thing means. This little thing right here, that sigma is called, that's the sum of, from math. You've probably seen that in math before. So this is the sum of the products. So first of all, notice that anytime you have a delta, it's always final minus initial. So in terms of a reaction, the products are the final and the reactants are the initial. So final minus initial. We're talking about the heat of formation of the things. So you're going to talk about the compound that's forming, the energy that it takes to form that compound. Don't forget that you have to multiply it by the moles in the reaction. So the N stands for the moles, and that's from the reaction, to get rid of the moles that's in the unit for the delta H. So really, this is the same thing we did yesterday. So you're going to add up all the products, the delta H's of the products, multiply each one by the moles in the reaction, and add them all up together. Do the same thing for the reactants. So multiply each one by the moles in the reaction, add them all up together, and then don't forget to do products minus reactants, and that will give you the delta H of the overall reaction. So what this means is, like in our last chapter or last lesson, we talked about how it requires energy to break a bond. So when you do a reaction, you have to break some bonds, and that's going to require energy. But sometimes you get more energy from the formation of the new things, and so the overall delta H of the reaction will be negative, and it'll be exothermic, even though you did have to break some of the bonds. So it's kind of like a competition. Did it take more energy to break the bonds, or did you get more energy by forming the new things? In whichever one of those magnitudes is greater will be the sign of the overall reaction. So whether the whole thing is exothermic or endothermic is based on which one of those was bigger. Don't forget, I have it starred down here, elements in their standard state are not included because it doesn't take any energy to form them because they're already formed. You're not putting them together, that they're just there. So elements in their standard state will be 0, and a lot of times on the AP exam, they expect you to know that. So they'll give you the delta H of the various things in the reaction, but they'll leave out the pure elements, and then a lot of people think they don't have enough information to calculate this because they don't know what the pure elements are, so you have to know that it's 0. So watch out that if you feel like you're short some information, it's probably that it's an element and that it's just going to be 0. And these are just some real world examples of why we're caring about enthalpy. Why do we study this? We need energy all the time, both in our bodies and to do things in the world. So combustion of fuels has to do with enthalpy. How much energy are we getting from the car engine that you're running? And then same thing in your body, that you use energy from your food. And so we can talk about the enthalpy that you get from your food and the energy that you get from your food for respiration. So that's it for chapter 6.